Okay, welcome back everyone. In the last lecture, we started studying sets. So we learned that sets are an ordered collection of objects, and you can actually perform operations with sets. For example, union, intersection, and complement. Okay? We also learned that sometimes we can list everything that's inside a set, sometimes we can't. And then usually we use a language description of the set. Now, what else? What else could we do with sets? Actually, one of the most important parts of mathematics is counting the number of things, the number of elements inside a set. Okay? This is crucial and is the basis for other mathematical important concepts in probability and in statistics, for example. So, because not all we cannot list everything inside all the sets, there will be some sets that we cannot list and then kind of count the number of elements, right? So for example, the set of the provinces in Canada, we can list it out and just count them, but most sets, they're too large. They can have lots and lots of elements. So it's difficult to list and it's difficult to count the elements up. So there is a part of mathematics, of finite mathematics, that takes care of counting or assessing the size of sets. And mathematicians came with some formulas that generalizes to any set. Now we're gonna start studying that. Okay, so let's first of all define a nomenclature that we use to mean to kind of write to mean the number of elements in A. So n of A is this nomenclature, is the way we point out that this is the number of elements inside set A. So n of A means the number of elements inside set A, right? So we can practice just with our reasoning. For example, what is the number what's the number of elements inside the empty set? Well, we can remember that the empty set is the set that contains no elements. So what's the number of elements in the empty set? Well, that number is 0. Okay? Here's another example. What's the number of elements inside the set composed of dog, cat, and fish? Right? So what's the number of elements of that set? Well, if you think about it, you have 3 elements. You have dog, you have cat, and you have fish. So you have actually 3 elements in this set. Okay? So these ones are easy, right? The empty set is obviously 0 because by definition it has no elements, and the dog, cat, fish set is really easy because we can list it out. But not all sets can be listed out, right? So that's why we're going to study some formulas that mathematicians came up with. And I'll try to justify some of these formulas, not all of them. I'll try to kind of show you why it works. In the next lecture, when we start talking about counting trees, then you will see that we will kind of understand why all of these formulas work, okay? All right, so the first one that I want to show you that it works is this one. And let's interpret what it's written here. So here, what we see is the number of elements, right? This n brackets means number of elements. And whatever goes inside the brackets is the set that I'm talking about, okay? So this part here is saying the number of elements inside a complement, right? Remember, a complement is a set, right? Is the resulting set of this operation of a complement, okay? So the number of elements in a complement is equal to take the number of elements in the universal set and subtract by the number of elements inside A, okay? So if we were to translate this formula, this identity to English, we would say the number of elements in the complement of A is equal to take the number of elements of the universal set and subtract to that the number of elements inside A, okay? Now, let's work out an example so that you can understand why this formula works. So let's say that I have a universal set, U, and I have inside this universal set, I have a set A, and also some elements that are not inside A. So let's say that I am analyzing all the students of this classroom and in my universal set, and inside set A are the students that use glasses, okay? Eyeglasses. So I have some students that does, some students that doesn't. In this case, I have one student that does, that it's residing, it's sitting inside set A, and I have 1, 2, 3, 4 that doesn't, right? Okay, so I'm considering 5 different persons. One is sitting inside, I'm using glasses, so here's the glasses. And the other ones are not, okay? So so I could ask you this. What is the number of people that do not wear glasses? So if A is the set of people that wears glasses, eyeglasses, a complement is the set of people that are not inside the set A, so they don't wear eyeglasses, okay? So because this is a simple example, I just could count it out, right? I could count, well, how many people? 1, 2, 3, and 4. Okay, so I just by assessing this example, I could say, well, there are 4 people here. Okay, but there will be cases that these sets are immense, and I won't be able to see this. So there's when we're gonna apply the formula, and it will make sense. So the formula says this: to find this number that I'm asking for, this number here, I need to get the number of people in the universe, or the total number of people that I have, and subtract the number of people inside A. So I'm going to apply the formula, okay? So this is the number, what's the number of people inside my universe, right? So this is the formula. So I'm going to substitute the number of people inside the universe with everyone that's inside the universe. So I have how many people? 1, 2, 3, 4, 5. I have 5 people. And I will subtract the number of people that wear glasses. Well, how many? Well, it's just person number 5. So it's just one person, okay? So in the end of the day, you will see that the formula will lead you exactly to the result. And it makes sense. Look at this. If we color what we want, let's color the A complement set. Well, the A complement set is everything that is not inside A, right? So I'm taking everyone. I'm taking the whole universe, but I'm not taking who's inside A. And that's exactly what this subtraction is doing. I'm taking everyone in the universe. I'm taking everyone here in the universe. I'm taking everyone in the universe. And I'm not taking, but don't take. So this subtraction means don't take whatever is in A. Don't take the number of elements in A. Okay? So I'm having the 5 people, but I'm disconsidering the one that wear glasses. Why is that? Because I want to know the number of people that does not wear glasses, that do not wear glasses. Okay? So this is the first formula. It's a formula that works for any set, right? We could name a set, I don't know, B, C. This formula extends to any set. Okay. Now, I will show you another formula. I will justify another formula. Again, I'm not going to justify all of them, but I'm going to justify this one here now. Okay. And sorry, not this one. This one is next lecture. Okay. The one I'm gonna work out now is the first one. So is this one here. Okay. So that's what I'm going to work out with you right now. So let's try to interpret what this formula is saying. What this formula is saying to us. Well, excuse me. The formula is saying this. Given two sets, A and B, right, in a particular universe, the number of the new set that is a result of the union operation between A and B. So you have a set A, you have a set B. Let's say that A is the set of people that like ice cream, and B is the set of people that like chocolate cake. Okay? So what this formula is telling us is this: the number of people that likes ice cream or chocolate cake, meaning the number of people that are inside this union or take it all, right? Hard copy everyone. So everyone inside this group, and you could have people that don't like ice cream, that don't like cake, so they're sad people, they're here, they don't like anything. But I want to know the number of people of this union, right? So I want to know how many people like ice cream or like or cake. This formula is telling that you can find this number by taking the number of people that like ice cream. You have to sum up with the number of people that like cake. But you have another term here that says, okay, but don't stop there. Subtract the number of people that like both. Okay? That's what this formula is telling us. So let's try to interpret. First of all, let's see what the answer would be. Because I drew this, and this is very easy. We could just count people up. So how many people are in the union? Well, let's make the union as we did in the last lecture. Well, the union is the result from getting people from A, okay, and getting people from B, okay? So this is the union. Just take it all. Take everyone. So let's say that we have Jack, Michael, Zach in group A, and we have Zach, Sarah, and Rolf in group B. Zach likes both ice cream and chocolate cake, but that's fine. I mean, I'm taking everyone. I'm taking Zach in A. I'm taking Zach because Zach is there. It's in the take it all deal. Okay. So if we count this out, we will have Jack, Michael, Zach, Rolf, and Sarah. 1, 2, 3, 4, 5 people. So this would be their answer if we were counting this directly. But we know that counting it directly doesn't work, right? Because this is a very, 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 very simple example. In real life, this is almost rare to kind of have important calculations that you need to do, for example, in probability that you could list off and count the set. Okay? So let's apply the formula. The formula says this: the number of people in the union, in the new set. So if we were to kind of draw a shape for the new set would be this orange part here, okay? It would be a bigger blob, kind of encapsulating everything in A and everything in B. And what you're going to do is you're going to take the number of people in A. Oops, let me go back to blue. The number of people in A plus the number of people in B. And it kind of seems natural, right? But there's another term here, which is take off the intersection. So let's apply this formula and try to understand why it works. So if I want to know how many people I have in the yellow kind of area, or in the orange shape, I can count the number of people of A. So I have Jack, Michael, Zach, 1, 2, 3 in A. I have 3 in A, right? Because I'm taking everyone, I will sum up with people in B. Well, B is Sarah, Rolf, Zach. So I have 1, 2, 3 in B as well, okay? And if we stopped there, the number of people would be 6, okay? But that's not the answer. Okay, that's not the answer. The answer is 5, and you can count them out. 1, 2, 3, 4, 5. Okay? What is happening? Well, think about this. Zach is part of the number of people in A, right? So Zach is one of these 3. And Zach is also being considered here as one of the 3 people in B. So you know what? I'm counting Zach 2 times. I'm counting Zach 2 times, right? I like to open this as, well, this is Jack, and this is Michael, this is Zach. Plus, this is Rolf, Sarah, and Zach. Well, but you know what? I already counted Zach. Zach is not two. It's not 2 persons. It's just 1 person. So this minus intersection means that I have to subtract the overcountings. Okay. So what did I do? Well, I overcount Zach because Zach is sitting in the intersection, because Zach is at the same time in A and the same time in B. Okay? So what the formula is telling me, don't overcount, subtract the number of times or the number of people you're overcounting, the number of elements you're overcounting. In this case, I'm overcounting Zach. So I'm overcounting 1 element, or the number of elements that sits here in the intersection that I'm overcounting. It's 1 element. So it's like, well, I have 3, and I have 3 Half plus Sarah plus Zach minus 1. So just, get rid of Zach because I already counted Zach. Okay? So in the end of the day, this is equal to 5. So this is the kind of visual, this is the visual explanation of why this formula works. And sometimes you want to find this number, the number of A union B, and you don't have it. You don't have to count, but you have n of A. You have n of A. You have n of B, and you have the intersection. So you can just come up with the final calculation. Okay. And if you take a look at, so this one we already saw, this formula for the complement. If you take a look at the second formula here, it's the same reasoning. The number of elements of A intersection B, so the number of elements sitting, so think about this, how many people are sitting on the intersection? Well, you take the number of people in A, you take the number of people in B, and then you discount or you subtract the whole, or like the union, okay? The take it all. And you can, I'm not going to do it, but you can reason using the same example at home. You can do this to kind of try to understand the formula, okay? So, and the last one we will kind of reason in the next lecture, okay? We will reason in the next lecture. Okay, so here's an exercise, and I'll give you some 5 to 8 minutes to try to do it. So this is a real world kind of example, okay? So in a behavioral experiment, participants could receive therapy A, therapy B, or both, okay? There are 60 participants in this trial, right? It's a behavioral experiment. 17 participants had a session of therapy A. So people that were kind of applying therapy A, they took a log of everyone. They kept track of every participant that had session of therapy A. And 33 participants had a session of therapy B. Okay? Now, I also know that from this 60, 42, the total number of participants received therapy. So there are some people that the people weren't eligible to receive therapy. Okay? What is the number of participants who did not receive both therapies A and B. So that's the question. Okay. We can we can tackle this exercise into two ways. First, we could use the De Morgan's laws that we saw, and then the size formulas, or we could use Venn diagrams, and we will see later that we will use counting trees to kind of solve these types of problems. But anyways, I will give you some minutes, and then you can try to come up with the solution. I will solve it both ways, okay? Yeah. Let me pause, just 1 second. Let me pause and I'll go there so that I can understand what you're saying. Let's start solving it using the formulas. So first of all, let's I'm gonna put here on the side information that the problem kind of that I can extract from the problem. I have 60 total people in therapy in the experiment. So that's the size of my universal set. People that received therapy A are 17. People that received therapy B are 33. And the other thing that they said is that the total number of participants who received therapy, so people that either received A or B, so take it all, people that received therapy, that's 42. Okay? All right. And the question is, what is the number of participants who did not receive both therapies A and B? So usually the questions are like a language, they are crafted in a language question, and you kind of have to translate it into a mathematical language, right? So the number of participants who did not, so the did not kinds of makes my brain go to the complement, did not receive both therapies A and B. So to receive both, someone has to be sitting in the intersection, okay? But actually, that's not what I'm asking for. I'm asking for people that did not receive both. So let me give me some space here. So what I want, I don't want this. I don't want the number of people that received both therapies. I want the number of people that did not receive both therapies. So I want the complement of this intersection operation. Okay? All right, so if we remember the formula for the complement. The complement is, well, take all your universal set and don't count people that are inside the set. Okay, so this is what the formula means. If we go back to the slide that contains the formulas, here you go. So this is the formula, N of AC. Let me copy this. I think it will be better. Now we can, so that we can actually use it for the solution. So here is the formula. I'm going to put only the formula up. So the formula says this: the number of elements inside a complement, whatever complement I'm talking about, right? here it was A, will be the universe minus, don't take whatever is in A, okay? Now, I'm not considering a set A. I'm considering a set A intersection B. So what I'm going to do is I'm going to modify this formula in that A is now A inter B. Okay, so A intersection B complement. So I'm kind of substituting A by A intercomplement, and the formula will apply. So take the number of things in the universe and subtract whatever is not in the set you're considering. Here you were considering A. Here I'm considering A inter B. So A inter B. Okay? That's the same formula, guys. That's the same formula. But here I pose it in a very simple manner. But whatever comes in parentheses is the sets that you're considering. This is called the argument, and it could be anything. So in this case, my set that I'm considering is not A anymore. So A appeared here and here because that was my consideration. Now my set in consideration is A inter B. So it will appear here and here. Okay, so we'll change the A to A inter B. And it makes sense if you interpret what it's telling you, right? So the number of things that are not in this set, take the whole, but don't count the ones that are inside the set. Okay? All right, so let's work out this formula. So this A inter B complement, this is the size of the union, the size of the universal set minus the size of the intersection. Okay, why did I continue with NA inter B? Well, I don't have that number to substitute. I have A union B, the number of A union B, but I don't have A intersection B. Okay, so I will have to find it. And the way to find it is to use another formula. So let me plot this here. Now I will be using, this formula here. Okay, so I don't have A intersection B. I will have to calculate A intersection B. So I'll call this formula here, this calculation number 1, and I'll halt the calculation there, and I'll say, okay, but I need NA inter B. So let me find this thing, okay? So I will use the formula here. The formula is already in terms of two sets, A and B, so I'm not changing the arguments. The arguments are the same. So this is take the number of people in A that did therapy A. So that's 17. So let me just copy the equation before so that you can have this in a more formal way. So this is NA inter B. This will be 17 plus, what's the number of people in B? Well, 33. Now, what's the number of people of the union? Well, I have that, and that's 42. Okay? So after calculating this, I will have 8, right? So this is the result. 17 plus 33, that's 50, minus 42, that's 8. Okay, so I can go back to 1, right? So going back to 1, I can finish my calculation. Okay, let me get some space here. Oops, sorry. I'm gonna get some space. Oh, Jesus. It's not what I want to do. This is what I want to do. All right. And there you go. I can even take this a little bit to the left. This a little bit to the left. And yeah. Okay, I think now we will have some space. Okay. So going back to 1. So going back to 1, I'm going to continue the calculation. So I stopped the calculation here. It was 60 minus NA inter B, but I found, so minus NA inter B, but I found that number. I found that number here in what I'm calling equation number 2, okay? So by substituting this value, it will result in 60 minus 8. So the number that I want is 52. Okay, so that's the answer that is expected. Okay, so in the test you could solve this in many ways. The formulas are very useful. You will have to know how to kind of deal with the mathematical equations, but you will always you will also be able to solve this using counting trees that particularly I think it's easier, but anyways, there are lots of people that likes to apply the formulas, and it's very important to have this skill. Okay. All right, so let's try to interpret this. The number of people that didn't receive both at the same time, okay, is 52. So I had people that received just A, just B. I had people that received the therapies at the same time. That's the intersection. What I'm calculating is what's the number of people that are not inside this, that receive therapy A and B at the same time. Okay, that's the interpretation. And now I want to solve it using the Venn diagram. Venn diagrams are not a good tool to solve this kinds of problem. I mean, for simple problems like this, they're very good. They're fast, but for bigger problems, and we will see that in the future, they are not good at all. So I will do it just so that you have a kind of a visual interpretation of what I'm talking about. Okay? Yeah. Come. Yeah, no, I'll do it now. Okay, so let's solve this using a Venn diagram, okay? So I have a universe, and I'm going to draw a universal set where inside this universe are people receiving therapy. There are some people that receive therapy A, and there are some people that receive therapy P. But we know that people can receive A or B, and there are also people that are not eligible to receive any therapy, right? Okay, there are some people that don't receive any therapy. There are some people that are sitting on A, there are people sitting on the intersection, and I mean, you don't need to kind of do this. Okay, it's just to visualize. Okay, so just visualize that. we have people that wasn't eligible for therapy. They're sitting outwards, A or B. There are people that received both of them. They're sitting in the intersection, and there are people that, for example, only received A, for example, this guy here, okay, or only received B, this guy here. Okay, so now that you visualize, I'm going to get rid of this because this is polluted and it will get in the way. Okay, well now, let's put some numbers in this Venn diagram. First of all, I have 7, so the total number of participants that had therapy A is 17. So usually I have to consider that everyone that had A includes people maybe sitting in the intersection. Okay, so the way I like to do it, just so that you understand, is I like to put the number 17 here. Getting all of my set A. People, the total participants that had session of therapy B are 33. Again, B can be all of this, right? So it can include this intersection. So the way I like to put the number is, well, I come here and I put, well, this is 33. Okay? All right. Now, the total number of participants who received therapy is 42. All right. So look at this. How interesting is this? The total number of people who received therapy is the union, right? So think about that. That would mean 17, right? People that received A, plus 33 people that received B. But think about it. People that were sitting in the middle, people that received both, are being overcounted. So let's say that Sarah here, she is part of the 17 and she's part of the 33, right? So if I sum 17 plus 33, right, that's 50. I'm overcounting Sarah. Okay, so I cannot do that, right? I kind of have to discount the overcounting. So if I have 17 plus 33, summing up to 50, but only 42 received therapy, how many are in the intersection? Well, 8. Only 8 are in the intersection. Okay? Because, well, if I were to overcount them, I would have 50. But only 42 received therapy. So I'm overcounting 8 people. Okay? So at the end of the day, after I defined this intersection, I can correct my numbers. So if 17 received therapy A and 8 are in the intersection, right? Actually, I have only 9 people that received therapy A. Only therapy A, okay? So 9 plus 8 gives the 17 that I need, okay? So 9 just received therapy A, okay? And that's they did not receive therapy B as well, but 8 received the therapy B. Okay, so 9 plus 8 gives me the 17 I want, and I can just get rid of that because now I have the correct things are accounted for. Same for here. Received a total of 33 received therapy B, and so only B, 8 received B and A, but only B, then we will have 25. Okay? Because 25 plus 8 is 33. Okay? So this 8 counts for the purple and counts for the orange. Okay, what's the question? Well, the question is, oh, and I also know that I have 60 people in therapy, in the experiment. So let's do this. 9 plus 8 is 17, plus 25, that's 42. Oh, good. This is exactly what I wanted. Now, the question is, what is the number of people who did not receive both A and B? Well, the people who received A and B is in the intersection. So the people that I'm interested in is here, is outside the intersection, is the complement of the intersection. Okay? This is the complement of the intersection. And I have this, but look, don't forget, I also have, this is not completely right, because I also have people that did not receive the therapy. So the people that did not receive A and B, they are not standing in the intersection. They could have received only A, so only A is 9. This is only A. Only B is 25, right? But I still have people sitting outside here, okay? Well, 9 plus 8 plus 25, there are 42. This is 42 people that did not receive therapy. So to get to 60, there are 18 people that did not receive therapy, any therapy, right? So I have to account for that once. So this is no therapy. No therapy. And so the answer will be, this is 9 plus 25. This is 24 plus 18. This is 52. Okay? That's exactly what is supposed, what we were supposed to obtain. Okay? This is practice, okay? I like doing Venn diagrams for simple problems with 2 sets. Again, this is not good for more bulkier kind of problems. You will see that. But it's very, very important that you practice with the formulas as well. Okay? All right, so we will continue next lecture with counting trees. Okay, I'm just gonna open here so that you can see. Just give me 1 second. Okay, so now I open the file. We will understand how to count. There are several techniques and good techniques to count the size of sets, but not only using the formula. This technique is called counting trees, and it's very, 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 very nice. So a tree diagram, and we will see this next lecture, I'm just going to kind of introduce the theme, is a rooted graph. Okay, so it starts from the right, what we call the node, the root node, or the universal side, the universal node, and it opens to the right. So the nodes can represent sets, choices, events, mathematical properties, whatever. Okay, we will use it to count number of elements in sets, right, in this course, but it could be whatever. Okay, the thing is, trees represent choices, represent a sequence of choices, right? A sequence of different possibilities. So what is consistent among all interpretations of trees is that branches from a node represent these different possibilities, okay? And paths represent the choices you made. So let me give you an example. Here is a tree. It's opening to the right. It's branching to the right. This is what we call the root node, or like the initial node. And it means that in this position you have two options. You can go with A or B. And if you go to A, then you have three other possibilities: X, Y, Z. If you're sitting here in X, let's say that you chose to come to X, you chose this path of going to A and then to X, you have another possibility, which is exclamation mark, right? So in this case, this tree is representing choices of, for example, characters, right, in your keyboard. The branches represents these different possibilities, right? If you're sitting in A, you have the possibility to go to X, to Y, to Z. If you choose to go to Y, then you have other two possibilities. You can either type exclamation mark or question mark, okay? And this kinds of structures will be way better than the Venn diagrams, right, for bigger problems. But we will adapt this concept of tree, of branches and options, to sets, right? So in our case, we're going to use a particular type of tree that is set up to be used with sets, okay? And that's what we're going to talk about in the next lecture. All right, thank you guys. See you next lecture.